All right, we've been talking about logarithms and exponential functions, right? And I thought maybe it might be fun. Would you mind if I tell a little story? Logarithms, IRL. I mentioned, I think, that I once used logarithms in my real life. I thought it might be fun to tell a little bit of a story when I used logarithms in my real life. This occurred maybe I don't know how long ago. It was quite some time ago, maybe 10 years ago for me. I realized that I have a genetic disease called hemochromatosis. Have you ever heard of this? So this is a true fact. Don't cry for me, but I have hemochromatosis. This is a genetic disease, which maybe you can tell from the word is about the blood. And this condition is kind of a fairly straightforward, recessive genetic trait, which exists almost entirely in Northern European white people. And it's one of these things you can be a carrier of the recessive trait and it doesn't affect you, but if both of your parents pass the recessive trait onto you, then you can have the real deal, which I have the real deal. And the recessive trait exists in something like 1 out of 40 white people, so maybe one of you has it. Maybe, Fairfield University could be a hotbed for this condition. And so that means if 1 out of 40 white people have the recessive trait, it means, if you do the math, about 1 out of 800 white people actually has hemochromatosis. That is, both of their parents had the recessive trait. And by some ridiculous coincidence, actually, both of my parents have hemochromatosis, and they didn't realize, all of us in the family found out that we all had this. So since both of my parents have it, that means me and my sister also were guaranteed to have it. Anyway, it's so hard being white, isn't it? Yeah. The reason that this exists in white people is because people with hemochromatosis, this is the upside, people with this condition are resistant to the bubonic plague, and this is why the condition became, most harmful genetic conditions should not exist for very long, because all the people who have them should die and it shouldn't perpetuate. But hemochromatosis is actually beneficial in certain situations. In modern times, it is not beneficial. But what it is too much iron. There's in a normal sort of healthy person, there is some kind of biological process by which extra iron in your blood is sort of flushed out of your body. But someone who has hemochromatosis, this iron removal thing doesn't happen properly, and so it means that my blood has far more iron in it than it ought to. And this is so the healthy. I'll tell you some numbers here. The healthy blood level, the way that they measure this, it's sort of like extra iron that is just floating around in your blood. The iron is used by the blood, but if you have too much iron, it just sort of hangs out and it's not incorporated into the blood cells. Extra, the healthy, they call this, the thing that they measure is called serum ferritin. And the healthy level is something about 20 nanograms per liter of blood. This is a very small amount. 20 nanograms of serum ferritin per liter of blood. And my level, when I sort of learned that I have this condition, mine was 800, which is much more than it ought to be. 800 nanograms per liter. And the effect of this is that you can live your whole life with too much iron in your blood, and it doesn't. It takes decades for it to accumulate, but eventually it can accumulate in your organs and cause your liver to fail, and you will die. And like some people who have this, most people who have this don't realize it until they're very old, and then it's like too late. I mean, very old, like in their 60s or 70s, but then their organs are all full of iron, and there's nothing that can be done. Another thing that can happen is like your feet and legs will turn orange, and this is actually like rust coming through your skin from all of the iron in your body. This has not happened to me. Nothing like that happened to me because I found out that I had it when I was, fairly young. But anyway, this is also a condition which, what is the treatment? So there is a treatment, although it's pretty primitive, I would say. As you know, iron is a chemical element. It's on the board over there, and that means that your body does not create iron, and your body actually also does not like break down iron, because an element is not something which can be broken down unless you have like a nuclear reactor or something. So anyway, the only way that iron enters your body is when you eat it, and the way that it leaves your body is by this, I don't know how it works, but anyway, someone with hemochromatosis, it doesn't leave your body. And so the way to remove iron from your blood is to remove the blood from the body. So the treatment is, every so often, I go and like donate blood, and they just like throw my blood away, and that procedure has removed some iron from my body, and I do that over and over again, and eventually it removes enough iron from my body. That's the treatment. So the treatment is called phlebotomy. This is really the only treatment. There are some like chemotherapy type drugs which can encapsulate iron and remove it from your body, but I'm not into that, right? Those have many harmful side effects. So phlebotomy is the treatment, right? And this is pretty like demoralizing somehow. I would go donate like a bag of blood, like a normal blood donation, but then they would just pick up this bag of blood right in front of me and dump it in the trash, because this blood has like too much iron in it to be used by somebody else. Anyway, phlebotomy is the treatment. Actually, hemochromatosis is less harmful to women. We don't need to get into the nitty-gritty, but perhaps you know there is a natural process by which women lose a fair amount of blood on a regular basis, and that actually helps for women's to not have too much iron in their blood. But this also is harmful, like women have more problems with too little iron. Anyway, for the same reason. Yeah, but this is the question. So the question that I had when I found out that I had this condition, my level was 800. I want, the healthy level is around 20. The question is, how many times do I got to do this blood thing in order to remove enough iron to get me down to the healthy level? So how many phlebotomies, phlebs they call them in the business, phlebs, it's phlebs. Do I need to get from 800 to 20? Right? This is the immediate question that came to my mind. And actually, this may tell you something about the kind of guy I am. As I was sitting in the doctor's office when he was describing all of this to me, it immediately came to my mind, I'm going to have to use a logarithm to figure out the answer to this question. What this has to do with logarithms or exponential functions. So first of all, you need to know exactly how much blood is removed from your body when you do one of these phlebotomies. And this is not a special kind of procedure. It's just like a normal blood donation. So when you, a typical sort of size and weight person, a typical sort of blood bag that you donate, blood donation, represents about 10% of the blood in your body. One of those bags it's about 10% of all the blood in your body. So every time I do this procedure, it will remove 10% of the iron figure from my body, right? So each phleb removes 10%. All right, so that means the first time I do it, I go from 800. Can anyone say what should it go down to after that? Of course, it's not exact, but this is approximately.
80.
Yeah, it should remove 80, so my level should go down to 720, right? That's because 80 was removed. Every time it's going to remove 10%. Right? And then the next time I do it, it would remove 72, which would drop it down to whatever, I don't know what. Right? And so on. You keep on doing this over and over again. Actually, each time you do it is a little bit like worse than before. You know, the first time you lose 80, the next time you lose 72. You're going to lose less and less as you do it every time. But anyway, can we figure out, I would like to write some kind of a function. I'm going to call it f of t. So I'm going to say let f of t be the ferritin amount after t times, all right? And so that means that f of 0, that is, if you do it 0 times, then the amount is 800. That's where we start. But f of 1 would be 720, like I said up there, etc. All right. Can we find a formula for this? F of t equals some kind of equation in terms of t. One way to think of this is you remove 10%, but actually it's a little bit better to think of, like more convenient mathematically, instead of removing 10%, you could think of it as keeping 90% and losing the rest, all right? So another way to think of this 720 is something like f of 1 would be 800 times 0.9, that is 90%, right? Whatever I had before, I keep 90%. And what would f of 2 be? Can anyone say, how would I? It's very similar to this, but make a little change. I keep 90%, that was the first time. And then I want to, again, the second time, keep 90% of what I had then. What would that look like by the formulas or whatever? Yeah?
Times 0.1.
Times, say it again?
Like 0.9 times 2.
Yeah, basically you want to multiply 0.9 again, right? So it would be, it's actually something like 0.9 and then times 0.9 again, right? You multiply, because this is what I had before in the previous stage, and then I'm going to multiply 90% of that again. If you like this, you could write as 800 times 0.9 squared, right? And then I think it's not so hard to tell. What would f of 3 be? Well, that means you do that again and you just get another 0.9. So this would be 800 times 0.9 cubed and so on. So generally speaking, etc. F of t, this is a formula for, I'll say 0.9 to the power t, all right? This is multiplication. There you go. This is a formula. This is a sort of classic, they call this an exponential decay. It's exponential because there's a variable inside the exponent, and it's decay because the level is going down gradually, all right? And the big question that I had at the beginning was how many times to get down to 20? So how many times to get to 20? The question means I set 20 here, and then I have to solve for t. Right? I want the answer to be 20, and I want to know how many times I got to do that in order to make it 20. All right? And how do you solve for t here? This is what we talked about last time. T is inside the exponent. The only way to solve when the variable is inside the exponent is by writing it with a logarithm instead. So in order, first, this is what we did last time. First, I want to isolate this part, and I'm going to do that by dividing 800. So this will say 20 over 800, whatever that is 0.9 to the power t. And now, what do we do to solve for the t? This is in the, well, I'm going to do natural log on both sides. Or you could think of as writing this in a logarithmic form, although it's not an e down there. I don't know if we did this exactly like this last time, but you take the ln on both sides. And then on the right side, we can use one of our properties of the ln. Remember, we had this property. ln of, something to the something is you do this, right? When you have an exponent inside of the ln, you can bring it down to the front. So that I'm going to do that on the right-hand side here. It'll say t, that business over there, 20 over 800, t ln of 0.9. And then we can just divide ln of 0.9. So t is this log divided by that. And all of those things on the right-hand side, you can just plug into your calculator and work it out. This I plugged into my calculator and I got 35.01. So that means in order to get down to the healthy level, I should do this phlebotomy 35 times. And so I asked my doctor, I did this kind of calculation. And I asked my doctor, how many times do I got to do this to get down to the healthy level? And he said, I don't know, maybe like every 2 weeks for a year. And that's kind of similar to this this answer here, and that's what I did. And now, so anyway, I used the logarithm in my real life. This was, I suppose, I could have done without this knowledge, but this is a nice example of an exponential function in real life. I did do the phlebotomy every 2 weeks for about a year, and then sort of, like right now, my level is actually approximately at the healthy level, and I have to go back and do this every few months to maintain the baseline. And I try to eat less high iron foods. But I love my frosted mini wheats, so that's difficult. Yeah. I asked my doctor also, should I just like not eat any iron? And they're like, no, because there is really no such thing as a healthy iron-free diet. Like, iron is present in all plant and animal foods. So if you want to avoid iron entirely, you're screwed. You can't. So it's better to just eat. They say it's better to just eat normal things and bleed it out every so often. If you eat it, you must bleed it. That's what I say. All right, any thoughts about this? I hope you don't mind a little my medical stories. This is the last medical story that I will tell about myself, or anyone else, I suppose. All right, anyone of you have a story to share? No? Okay, great. All right, let's talk some more then about exponentials and logs. This is maybe the last day that we're going to be talking about this. I don't know if we'll quite make it through everything else that we had to say, but the last thing that I want to talk about is logs and exponentials with other bases. Other meaning other than e, right? We've talked about the natural log and the exponential function with base e because they have the most convenient properties when it comes to calculus. But there are, I'm sure you all know, there are logs and exponential functions with different bases. Actually, in this example right here, this was an exponential function, but not with base e. This number down here is called the base, and in this case it was 0.9 rather than e. Logs and exponential functions with other bases, right? So e to the x is the natural exponential function. But there are other exponential functions. We also have, things like 2 to the x or 10 to the x or 0.9 to the x, right? These do come up in real life, like the 0.9 to the x. It was in my example. All right. Now, these are probably things that you've have experience with exponential functions in the past. Although there is something slightly weird about these, and that is that I will say they're a bit weird to define. For example, like when you're a kid, somebody told you what 2 to the power 3 means. What does it mean? I'm sure somebody explaining this to a kid, if my kid asked me what does 2 to the power 3 mean, I would say that means 2 times 2 times 2, 3 times, right? That's what 2 to the power 3 means. And I think everybody understands what that means. What about 2 to the power 1/2? This is actually different. It's not, you wouldn't explain it in the same way. You wouldn't say, oh, this is like 2 times itself 1/2 of a time. That doesn't make any sense to say that. But we all know this is actually the square root of 2. So this is like 3 times, right? That's how you describe what 2 to the 3 means. But when the exponent is not a whole number, it's not described in that same way. When it's a fraction like that, you describe this as some kind of root, right? Like 2 to the 1/5 is a 5th root. Or something even more complicated, you can have a combination of these, right? Something like 2 to the 3/7. This is defined to be the 7th root of 2 times 2 times 2. So when you see weird fractions up there, what it means is the denominator tells you what kind of root it is, and the numerator tells you sort of how many times you write the number, all right? Slightly weird, but not so bad, I guess. What about, here's what's really weird. 2 to the power pi, something like that. I'm sure everybody knows pi is an irrational number. That means you cannot write pi as a fraction. And so what are you going to do with that? Apparently, since it's not a fraction, this actually is not some kind of root of anything. Anybody happen to know what is that? Or is it any, can you even do that? Anybody tried this on your calculator? Your calculator will give you an answer. Like there is such a thing as 2 to the pi, but it's not anything like this. And that's why I said at the very beginning, they're a bit weird to define, right? You can define them for whole number exponents, no problem at all. For fraction exponents, it's a little weird, but not so bad. For irrational exponents, though, I will just say this right here, not clear what this even means. Right? It does mean something, but I'm just trying to say it's not obvious at all what that is supposed to be. And so so this is what I meant when I said 2 to the power x as a function requires some special definition. For some values of x. For instance, x equals pi, right? If you show this to your friends at lunch, do you really understand what 2 to the power x means? They're like, yeah, sure, it's like 2 times itself a bunch of times, right? The answer is like, no, you idiot. Or it's something that everybody feels like they understand, but actually if you think closely about it, you realize there's some things that are very strange about this. If you allow x to be any number, then you're going to encounter weird situations like this, where it's not obvious at all what the definition is supposed to be, all right? 2 to the power x requires some special definition for some values of x. And so I'm about to tell you the definition. This is weird, but it is necessary because there's no better way to make this definition. So given, this is our big definition here. So this is given any base b, and I will say b must be positive for reasons that you will see immediately. The base is this number down here. So I was talking about 2, but of course you can do this. It doesn't matter if it's 2 or something else. Given any base b, we define b to the power x. This is the definition of b to the power x. It is e to the power x times ln b. All right? This is the definition So maybe one of your friends will say at lunch, oh yeah, I know what 2 to the power x means. It means e to the x times ln2. That actually is what it means. All right, given any base b, we define this. And this actually is the reason why we have been taking what I've described a few times as a somewhat weird approach where we define the log first and then we talk about the exponential functions. It's actually because of this. In order to define what b to the x means, you have to already know what the ln of b means. And we do know what the ln of b means. It means the area under the curve of 1 over t from 1 up to b. All right. If you don't already know what the ln of b is, then you really have no way of making this definition, or it becomes kind of like a circular definition, which most people in high school don't really care about being very particular about getting the definitions right. But this is the way to do it without using some kind of circular reasoning in your definitions. All right, b to the x is defined as e to the x times ln b. So what does 2 to the pi mean? So 2 to the pi means e to the pi ln 2. Make sure you put everything where it goes. And that has a real definition. ln 2, of course, is a number. Pi is also a number. You multiply them together up there. And then how do you do e to some weirdo power? Well, e is defined to be the inverse function of the natural logarithm. And so e to some weird power, you write it in logarithmic form, and you can figure out the value that way. All right, your calculator, of course, does all of this automatically. Your calculator already knows how to do this kind of stuff. So you don't really have to think it through at all. All right. Anyway, this b to the x, I'll write it again, b to the x, the definition is e to the x ln b. This is called the exponential function with base b. Everybody knows that. With base b. I said before the b must be positive. The reason is because I am plugging the b inside of the natural log, and as we've already seen, you can't plug a negative number into a ln. And so in order for this to work at all, the base b has to be positive. And they're actually using negative bases. There really are serious problems with putting negative bases in exponential functions, so we don't even talk about that. All right, there are similar rules for b to the power x. So I will say we get the usual, and we don't need to spend too much time on these. The usual rules, they are things like b to the x plus y is b to the x times b to the y, right? Also, b to the x minus y is b to the x divided by b to the y. These are the standard rules that you all know for exponential functions. B to the x to the y is b to the xy. And one last one is this. ab to the x is the same as a to the x, b to the x. All right, these are the usual rules for exponents that you have known for several years, I'm sure. I would just like to point out, though, these can be justified using the definitions. So we don't need to go through all of these, but we can prove these from the definitions. I want to do one, and then I want you all to try one. We can prove these from the definition. How about b to the x plus y equals b to the x, b to the y, right? I want to prove this. I start with the thing on the left, and I'm just going to simplify it somehow using the definition, hopefully end up with the thing on the right. When you're writing a proof like this, don't write both sides of the equality like where you started. That's what I'm trying to show. I should start with the left-hand side. I'm going to write a bunch of stuff, blah, 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 eventually ending up with b to the x, b to the y. That's what I'm trying to fill in the intermediate steps. What can I do with b to the x plus y? Well, I said from the definition. I will refresh your memory. The definition is b to the x equals e to the x ln b, right? So from the definition means I plug into this definition here. b to the x plus y is e to the x plus y ln b, right? That's the definition of b to the x plus y. Anybody want to suggest? I want to somehow simplify that and hopefully end up with what you see at the bottom. Anybody have a suggestion? What can we do to simplify there? What do you think? Yeah?
Do you distribute that LNB?
Yeah, distribute. Yeah, I don't know about you. When I see like parentheses next to a multiplication, I start feeling something in my bones. I want to distribute here, all right? Even if you don't know what's going to happen. I mean, that's really the only thing that you could do looking at this. So when I distribute, it'll say e to the x ln b plus y ln b, right? Can we do anything with that? Perhaps using some property of ease. We actually have properties of the exponential function. And there was one property about what if I have e to something plus something, both added inside the exponent. Anybody remember what this is? I'm going to use a property of e to the x here. Anyone recall? If you have addition inside the exponent, what is that? What can you do with that? Maybe you don't recall. If you have addition inside the exponent, we had, if you look at your notes from last time, it was something like e to the a plus b is e to the a times e to the b, right? This is the property that I'm going to use here. So e to the x ln b plus y ln b becomes e to the x ln b times e to the y ln b. And then those directly gives you these, right? This is, again, the definition. E to the x ln b, that is b to the x. That's what b to the x means. And e to the y ln b, that is b to the y, right? That's how we do it. Shun. This is what I like to write at the end of a proof. I have a 100-year-old math book and they say shun at the end of the proofs, which I think is silly. That's why I say it too. All right. I got one for you to try. See if you can do a very similar kind of simple, this proof, I would say this is a simple proof because you don't really need to have any ideas. You just kind of like simplify stuff in the normal way and it all works out. I suppose you have to remember about this property. But how about you try the last one there? Try a to the x, what was it? ab to the x, sorry, equals a to the x, b to the x. So your proof should begin with ab to the x equals something, something, something. You should start by using the definition of what ab to the x means. See what you think. If you get it, you can write shun at the end, but you don't have to. Your first step should be to turn this into e something something, using the definition of what the power means. Your first step is really going to be that red thing at the top there. But using AB instead of B. thing. All right, can we talk about this? It looked like people mostly ended up arriving where it ought to be. So here you begin with the definition of ab to the x is e to the x ln ab, like that. And then most people eventually remember there's a property of the natural log. Ln ab is the same as ln a plus ln b, like that. And then we can distribute the x, just because what else are you going to do, really? It'll say e to the x ln a plus x ln b, right? And then the rule about e to something plus something, this splits up as e to the x ln a times e to the x ln b. And those, each of them, just the definition, this equals a to the x, and this equals b to the x. Shun. All right, I think pretty much everybody ended up with something that looked like that. Great. This also I would describe as a fairly simple proof. You know, we're not going to do a lot of proofs in this class, but I know some of you at least are going to be math majors or are already math majors. This is gotta put some proofs in there, right? I, as a mathematician, have a deep and abiding love for proofs. This is a fairly straightforward one. Any questions about that? You could similarly do, you know, these are 4 different properties. All of them can be proved in a very similar way. If you're looking for something to do tonight, all night long, do some more of those proofs if you like. All right, we got about 10 more minutes left. I think we can talk about how about derivatives and integrals using these other exponential functions. Derivatives and integrals with b to the x, right? This also is something that is fairly easy to work out using the definitions. So if I want to do derivative of b to the x, using the definition of b to the x, this is the same as e to the x ln b, right? And I can do that because we already know what the derivative of e to some power is. It is just the same thing again, and then you have to use the chain rule. So here, derivative e to the x ln b is e to the x ln b. That is, you get the same thing again, and then times, now I have to do the chain rule, multiply times the derivative of the inside being that thing. So this thing, its derivative, x times ln b. This is a little strange, but really this is just x times some constant, right? And so what's the derivative of x times a constant? It's just the constant, whatever it is. This is, it's written in a weird way, but this is just like if it said something like 2x, the derivative would be the 2. The x goes away. The answer is just the constant part. So here, the constant is ln b, all right? And that's what the derivative is. It's usually you won't see this formula written in that way because usually they would write this back as b to the x, right? E to the x ln b, that is b to the x. And so this is like that. And this is the way that this formula is typically written. I'll put it in a box here. And you need to know this formula, b to the x times ln of b. All right, that is the derivative of an exponential function other than e to the x. If it was e to the x, you just get e to the x. If it's something else to the x, you get this thing with the extra little ln b there. All right, so for example, how about what's the derivative of 4 to the x? Just plug directly into the formula, it would be 4 to the x times ln 4. All right, that's a very, very easy one. More likely on the homeworks or quizzes or whatever, I would ask you to do a more complicated derivative, something like, how about 4 to the 3x squared plus 7x to the 5. All right, so to do this one, you again are going to use, you know, what you see in the box is the basic idea, but you also have to do the chain rule here because I have some fancy business on the inside. And so I'm going to do what it says in the box is you start with some b to something, you get the same thing again times ln b. So I'll do that part first. The same thing again, times ln b, which in this case is ln 4. And then, so that's using the formula in the box. Then we have to do the chain rule right here, times this, what I'm about to write here would be the derivative of the inside. Can anybody say what's the derivative of the inside? The inside, of course, means, in this case, the inside of the exponent, that stuff up there. Somebody want to shout it out? What's the derivative of the inside stuff? 6x plus 35x to the 4. Yeah, great. So this is the derivative of that weird looking thing. All right, how about this? You try, this will only take you a moment, but see what you think. I'll just give you a moment. I don't even need to walk around. See what you think about that. 8 to the power negative x squared. The derivative. Anybody want to say what you think? What did you get? Maybe someone I haven't heard from lately. Any? Yeah.
8 to the negative x squared times ln 8 times negative 2x.
I like it all. Yeah. Excellent. Yeah, that's exactly what I got. Any questions about that? I hope that this all sounds good to you. Here's a question. Of course, you can re-simplify this in some other way if you'd like. Can I bring the -2 and combine it with the 8 and make this negative 16 to the power whatever? The answer is no. You cannot combine constants in that way. A constant multiple does not get absorbed into the base of an exponential function. Like this 8 right here is very different from 8 times something or other. It's an exponential function with base 8, which, as we've already seen, is a kind of a weird thing. It has a weird definition, and it does not play nice with a constant multiple here. You could write the -2 first, but you cannot combine it with the 8 in any kind of ordinary way, at least. All right, excellent. What about the antiderivatives? We got just a few more minutes, but this is no problem. So our formula for the derivative says derivative b to the x is b to the x ln b. One way to sort of think this through in words is just when you do the derivative of an exponential function, you get the same answer again, but you have to multiply times this extra constant, ln of b. What about the antiderivative then? If taking the derivative means you get the same thing, but you multiply by this constant, the antiderivative also should give you the same thing, but you divide by the constant. It's the same procedure, but just kind of inverted or backwards somehow. So this automatically means the integral b to the x dx is, I will write it this way, b to the x divided by ln b. Or sometimes, I should say, plus c. Don't forget the cupcake. Sometimes you see this as 1 over ln b times b to the x, but that's, this is the antiderivative formula. All right. And, this works out. I mean, there's not much interesting to say about this. How about, let's just try, we've got a few minutes left. How about the integral of x times 7 to the 3x squared? All right. This is a little weird. So you cannot just plug directly into the box for this one because it's not just 7 to the x. In that case, you could just plug straight into the formula in the box. It is instead some more complicated stuff inside there. Anybody want to suggest that what should we do to handle this? It doesn't match the box exactly, so we're going to have to do something. When it comes to integrals, actually, we don't have a lot of tricks at our disposal. There's one integration trick that comes to mind to me? Yeah?
You make the 7 to the 3x squared u.
Yeah, we have to do the u substitution. There's really no other thing to do here. And as usual, I'm going to choose the u to be the inside of something. Anyone want to suggest what should the u be here? Yeah? Yeah, let's choose u to be 3x squared. The inside of something is usually what you want the u to be. And in this case, the only way that makes sense is to choose the inside of the exponent. You don't also want to include the 7. It'll get messed up if you do that. So u is the inside of the exponent. That means, all right, this is a pretty ordinary u substitution. The du will be 6x dx, right? And I'm going to divide the constant across like I usually do. 1/6 du equals x dx. And then let's try and plug the stuff in here. I get x 7 to the u dx. And if I put the x's together, just move stuff around. 7 to the u times x dx. And then x dx is 1/6 du. That's what I said before. So this is 7 to the u times 1/6 du, like that. Factor the 1/6 out of the integral, and then this will be completely as simple as it's going to get. Integral 7 to the u du, like so. All right? That was a more or less ordinary u substitution. And then to actually do the integral, we do the thing in the box. Now you can actually use the formula up there. All we have is 7 to the power u. And so, well, we have 1/6 from before. But anyway, I'm going to write the formula in the box. 7 to the u becomes 7 to the u divided by ln of 7 plus c. Make sure you put the b's and the x's in the right place. It's not ln x on the bottom, it's ln b on the bottom. All right. And then as always, the last step, I'm going to replace the original variable. So my final answer is 1/6 times 7 to the power 3x squared divided by ln 7. There you go. All right. You'll have some more practice with these on the homework. This is all I want to say about exponentials with different bases. Last thing to talk about in all of this would be logs with different bases, and I guess we'll do that starting next time. Hope you all have a good weekend, and please let me know if you want to try some of these quiz questions again. Maybe wait until you see how you did, but send me an email, we can set it up. Just tell me, at least tell me the day before. Don't just show up in my office and say I want to do this one, because I have to make up a question or whatever. But I look forward to it.